Good afternoon. So this might be actually the scariest initial screen of this class. But before we say anything about it, let me point it out that those of you who are my students taking this class, you don't need to write this down. We're going to just go over what I wrote, and I'm going to point out some of the important things. Because there is a handout I will provide in Blackboard with all of these guidelines. So what we want to do in this lecture is to discuss a little bit the example we did last time. So remember the method of separation of variables, which is the method we're going to use till the end of the course. I introduced that method actually by working the method with an example. So in the previous lecture, we actually did solve the wave equation y partial t twice equals y partial x twice. So in this case, a is equal to 1, that constant that usually appears in front of yxx. And I'm going to actually refer back to that solution on the next page just to comment on this a little bit. Now, what we want with this page here, with these guidelines, is to provide the overview of the method of separation of variables. Unlike what you might have learned from ordinary differential equations, these are guidelines, because you will see that even if the PDE is linear and homogeneous, it's not guaranteed to be actually separable. So when it works, these are the steps basically you have to go through with this method. In general, there are exceptions, that may not work in some cases. And for the method to work, there are some critical aspects in all of these steps that need to happen. So that's what I want to talk about. So again, once again, if you are my students, you don't need to write this down. Just pay attention to what I'm talking about with all of these items here. So we start the problem obviously with confirming that the PDE is linear and homogeneous. So there's no guarantee that the separation works, but for sure it's not going to work if it's not linear. So you want a PDE that is linear and homogeneous, the PDE itself. Then it's crucial to spend some time before you attack the problem to analyze the boundary and or initial conditions. I'm saying and or initial conditions because there are situations when, for example, a problem may not have boundary conditions. You will see why that's the case. It really comes sometimes from the physics of the phenomenon. I mean, like the shape of the object and how the physical process works, so that basically you don't need anything besides some initial condition. Furthermore, remember in some other problems, we just have boundary conditions basically, because if there is no time variable, like in the steady state temperatures problems, we may have a problem without time variable, then we just have boundary conditions. So you can proceed with the method if you have the following conditions on this boundary and or initial conditions. So if you do have initial conditions, then you must have all boundary conditions linear and homogeneous. So this is crucial because this is what creates that all-important problem, the so-called Sturm-Liouville problem, which is one of the two ODEs, ordinary differential equations, that come to be when you apply the method. Roughly speaking, you need basically linear and homogeneous conditions so that one of the two ordinary differential equations ends up being a homogeneous boundary value problem. That's the key thing. In most of the examples, you have typically homogeneous boundary conditions, a non-homogeneous initial condition. That's what happens usually in the examples we talk about, like in the heat or the wave equation. If you remember in my previous example, we had homogeneous boundary conditions and two initial conditions. One of them was the velocity, which was also homogeneous. And then the only non-homogeneous condition was the initial displacement. If there are no initial conditions, then all but one boundary condition should be linear and homogeneous. So basically, you can afford essentially one non-homogeneous condition. On the other hand, part C, we will deal with this later in the course. Not much later, but in a couple of lectures or so. if one or more boundary conditions are non-homogeneous but constant, we can actually transform the problem into a homogeneous one by making a change of variables. So we will deal with that later. For now, we're going to stick to homogeneous conditions. Then in the part 3, we're going to assume that the solution takes the so-called product form. Basically, in the example we did before, we took the displacement to be a product of a function in little x and a function in t. You need to plug in the product form into the PDE, and if possible, of course, separate the variables and introduce a separation constant. Typically, we denote that by minus lambda if we anticipate that that's practical, that lambda is positive, or the way usually in most of the examples, by denoting that separation constant by minus lambda makes the algebra more streamlined. And at this point, you're going to stop if you realize, as I'll show you with an example in the next page, you're going to stop if you realize that you can't actually separate the variables. But if you do separate the variables, then you're going to obtain two ordinary differential equations. The next step is to plug in carefully the product form into the homogeneous boundary conditions, carefully, and always assuming that you're looking for non-trivial solutions. And when you apply the product form into the boundary conditions and you compare them to the two ODEs, one of them becomes a boundary value problem, a homogeneous boundary value problem, I should have said here. This is the so-called Sturm-Liouville problem, or the eigenvalue problem. So you solve it and you obtain the eigenvalues and the eigenfunctions. So I should pause here to mention that at this point the method works if this boundary value problem ends up being one of these so-called Sturm-Liouville problems. So in other words, it should give you infinitely many solutions, or should I say infinitely many eigenvalues, and corresponding to them, infinitely many solutions, right? You're going to have infinitely many lambdas, which will lead to infinitely many x, right? In this case, big X of little x, as in the previous example. And moreover, those eigenfunctions should be orthogonal, right? I mean, in this case that we talked about last time, those functions were sine of x, sine of 2x, dot, 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 sine of nx, which we know they are orthogonal, and they make what we call the Fourier sine series. Because if they're not orthogonal, they are useless for what comes later in the problem. You won't be able to find a series in terms of those functions if they're not orthogonal. And I'm mentioning this because in different contexts, like for example in spherical or cylindrical coordinates, you have different types of eigenfunctions. So when we get to those functions and they're not sine or cosines, the first thing we're going to check is to see if they are orthogonal. Because if they are, then we can come up with series representations in terms of those functions, and therefore the method will work. The only difference is that your solution won't involve a series of sine and cosine, but other functions like Bessel functions or Legendre polynomials. The next step is for each eigenvalue obtained at 6, so the previous step, you're going to solve the other ODE for each of those eigenvalues. That's why from this point on, you're going to index those notations with little n. So for example, when you solve for big T, you're going to call that solution T sub n of T, because that's corresponding to each eigenvalue, lambda 1, lambda 2, lambda n, and so on. The next step is you're going to use superposition to obtain a linear combination of the solutions already found. So you have infinitely many solutions already found. These pairs of big X and T, Xn and Tn to be more precise, right? So you're gonna end up with combinations of these. Each of these product is a solution, and you're gonna obtain an infinite series with coefficients to be determined. Linear combination, right? That's the idea. So the very last step is to find those coefficients, and you do that by applying the remaining non-homogeneous conditions to the series found in the previous step. This is the moment when you're going to end up with having these coefficients come from a series representation like a Fourier series in our case. This is essentially the framework of all the problems we're going to deal with variations, of course, to deal with non-homogeneous terms and other wrinkles like this. For now, let's actually analyze a little bit more the solution obtained in the previous lecture. And for the remaining part of the lecture, I want to do, I'm going to go over two examples just to show you how one can be separable and one cannot be separable, although both are linear. And I think I'm going to leave it for that in this is going to be probably a short lecture. And then later on, we're going to obviously go through more examples of separation of variables. From now on, you should have these guidelines printed out in front of you just to see how each step applies as we move along. So stay tuned for the next page. All right, so last lecture we solved this boundary value problem representing a wave equation. This is the general format of the wave equation. And so therefore in our example, A was equal to 1. I want to point out how this solution we obtain actually fits our general solution for the wave equation, because remember we show that any wave equation, if just disregarding for now any initial or boundary conditions, any wave equation has a solution in the form of those so-called traveling waves. Some function of x plus at plus some other function psi of x minus at. So I want to point out that the issue is that we can't really find phi and psi by classical means or traditional means, however you want to call it, in terms of typical functions, in some cases when you have other types of boundary conditions. So we managed to find phi and psi in some easier cases when we didn't even have boundary conditions, right? When the vibrating string was infinite. Nevertheless, if we have a solution in the form of a series, that solution should still fit the overall framework of the fact that this wave equation should be the sum of these two functions. So let's actually confirm that that's the case. This isn't something we need to do. I just want to point out that the two theories the two results don't contradict each other, if you wonder. So in the previous lecture, we showed that the solution of this boundary value problem here was y of xt equal summation from 1 to infinity to minus 1 to the n plus 1 over n sine of nx times cosine of nt. All right, so this is essentially the trade-off of this method. Your solution will be always a series. So it will be a function in the form of a series. And now, does it follow the fact, does it follow from this that it can be written as a sum of two functions, one in x plus at, one in x minus at? I should say here that for this case, when a is equal to 1, you would expect the function to be, the solution to be f of x plus t, or phi of x plus t, plus psi of x minus t, right? Because a is equal to 1. So the answer is yes, and it comes from a simple trigonometric formula, which we actually used it in a different problem earlier. So sine of a cosine of b is actually 1/2 sine of a plus b plus sine of a minus b. So we can apply this formula for our solution. Let's see, sine equals b. All right, so that's going to be 1/2 sine of nx plus nt plus sine of nx minus nt. The two cancel, and now we can split this summation into two summations. Minus 1 to the n plus 1 over n sine of, and here we can pull out n if you want, sine of n quantity x plus t plus the summation from 1 to infinity minus 1 to the n plus 1 over n sine of n quantity x minus t. So you could call this one phi of x plus t, the first traveling wave, and this one psi of x minus t. So again, it's not that these traveling waves don't exist if we use the separation of variables. It's just that we don't usually have them in terms of a traditional function, basically. That can happen maybe if you have easier boundary conditions to deal with. Well, even better, no boundary conditions. In that case, you have a more straightforward solution of the wave equation. In most of the other cases, the separation of variables method is the way to go. So that was just a remark related to the previous lecture. Let's continue with two other examples that I want to check to see if they are separable. So let's see, let's look at the following example. Let's say you try to apply the method of separation of variables to the following PDE, and I'm not going to even attach to any meaning to it, like any physical meaning. So we have just a function of u x t, and then the PDE is x plus t times u partial x twice minus u partial t equals 0. You could probably attach some sort of a meaning. This looks like a heat equation if you rearrange the terms. It's a heat equation in which those physical constants are not constants anymore, right? And they depend on the time and the location of the bar x. But let's postpone for a moment any possible interpretation of the problem. The goal is to see what happens if you do step, what was it? Step 4 in the previous page, when you try to figure out if you can separate a variable by assuming that the solution takes the form of the product of two functions, one in little x and one in little t. Now notice this is still homogeneous and linear, right? So the PDE itself satisfies the first condition. It's homogeneous and it's linear. Remember, the coefficients of u can depend on x and t. But let's see if it's separable, if we try to separate x and t. Well, if I apply the product form, u partial x twice becomes x double prime of little x, big T of little t, and then minus u partial t becomes x x of little x times t prime of t equals 0. So, well, let's see if we can separate it. So let's move one term to the right. And I should warn you, and at this point again, just for convenience, you can just write x double prime and big T, because we assume we know that big X depends on little x, big T depends on little t, so we could use those shortcuts. And remember, if it's not separable, it's not like you have a rule to check. You just basically stare at the problem and you realize that there's not much you could do to move the terms algebraically, to use any algebraic trick from left and right, so you could separate the variables. For example, we could maybe divide by t and divide by x on both sides. So you could have, for example, x plus t, x double prime over x equals t prime over t. This is the sort of step you will do at this moment. But the problem is that you need essentially this guy here only in x and this guy here only in little t. There's no way to move t on the left side without bringing x as well. I hope it's clear from this point on that this is not going to be separable, right? If we have, for example, x times t or something of the sort, then we could move little t together with big T, and that will have been just in terms of little t. But since it's a summation, we can't really separate little x and t from that parenthesis. You can move that parenthesis left and right, but you still have both x and t. So that's an example when the equation is not separable. And on the next page, I'm going to show you another example, which I won't solve for now, but it will be a good idea actually if you tried it. It's actually doable, although it's a more cumbersome one, so you probably want to do it maybe later after we go over other examples. I might get back to it later on. But that's another example in which that one will be actually separable. So let's stay tuned for the second page. I mean, not the second, will be the third page. So let's take a look at this example. This would be like a wave equation with some damping. If you remember from ordinary differential equations, the damping force was proportional to the velocity. So basically you have the component of the equation that's just due to the elastic force, yx twice here, and then this guy here, the last term in the equation, will be, for example, the damping component. This will still be homogeneous and linear, and we could still try to see if it's separable or not. And just like before, we take the product form, and again from now on you can just write just x times big T, always remembering that big X stands for big X of little x, big T stands for big T of little t. So then we plug in the product form into the equation. So we have x t double prime equals x double prime big T minus a big X t prime. All right, so let's see how we can separate big X and big T, right? So we can combine these terms here. If I move that guy to the left side. Remember, look, there are no standard steps. I hope it's clear. It's just a little bit of practice on this point on, right? I mean, to see which algebra steps you need to do. The goal, remember, is to come up with an ODE in a big X and an ODE in big T. You want to also keep the derivatives on the top of the fraction. That's also important because you may recognize when that happens whether you actually have an eigenvalue problem already solved, which is very important to speed up the process. So when you reach this point here, we can divide obviously by big X and by big T. And so that means on the left side now I have T prime plus T double prime over big T. And on the right hand side, X double prime over big X. So it is separable, and as soon as you manage to separate it, introduce that separation constant, which, remember, we typically call it minus lambda because in most of the cases that's the practical notation for the eigenvalue. Now in this case, let's say we have some initial conditions and boundary conditions. So suppose the problem has, in addition to the PDE itself, obviously, let's say it has an initial condition, initial displacement in this case. Let's say the initial velocity is going to be 0, and boundary conditions, just like before, y of 0 equals y of pi equals 0. So Dirichlet type of conditions on the interval 0 pi. As soon as you separate the equation, remember the next thing to do is to plug in the product form into the homogeneous boundary conditions. So you can leave the initial conditions for now, and then you look at the boundary conditions and plug in the product form. So y of 0, I'm sorry, I should have said here, let me write that down again, I forgot the t. Y of 0t, y of pi t equals 0. So y of 0t is x of 0 t of little t. That should be equal to 0. And then x of pi big T of little t is equal to 0. Because we're looking for non-zero solutions, non-trivial solutions. For this to be true for any t, any little t, it implies that you must have x of 0, x of pi equal to 0. This is the moment when you realize which of the two ODEs is the eigenvalue problem, or the so-called Sturm-Liouville problem. Now, with a little practice, you will realize from immediately, like, you know, earlier than this moment, that this is going to be the one in big X, because you will recognize a previously solved Sturm-Liouville problem. So that's very important to, unless the problem is asking you to do the whole work, it's very important to recognize that one of the ODEs, x double prime plus lambda x equals 0, together with the boundary conditions, x of 0, x of pi equals 0, is already solved. You will get it from tables of Sturm-Liouville problems. So you don't do it one more time. You save a lot of time, obviously, right? You don't have to, again, take all the possible cases. You know already that the eigenvalues for these problems are lambda n equals n squared, and then the eigenfunctions xn of little x is sine of nx for n from 1, 2, 3, and so on. So a big chunk of the work is already done for you, because see, these Sturm-Liouville problems are the same for a larger class of problems. And then what you have to do in this case, and we're not going to do it right now, but what you have to do is to just move on to the other ODE, t prime plus t double prime over big T, plug in the eigenfunction, so minus lambda is actually minus n squared, simplify a little bit, multiply by t, move the terms around, plus n squared t equal to 0, and you're going to solve and find tn, right? Because you solve an ODE for every n, so that's why you call the solution tn. And at this moment, any constant is denoted by an, bn, any constant of integration, because again, it depends on n. And then you move on to impose the remaining homogeneous condition. In this case is the velocity. And then at the very last step, you're going to impose the non-homogeneous initial condition, which will lead to a series representation. So we're going to have plenty of examples of this type. Just keep in mind that it's extremely important to go slow in the beginning when you arrange the problem, to make sure that your eigenvalue problem is the correct one, to make sure you can recognize it if it's one of those already solved, so that you can already start with the eigenfunctions and the eigenvalues on the next step. So I think that's it for today. I'll see you next time.